Hello everyone, and welcome to Lesson 4. In this lesson, we will cover Section 2.2 of the Logic Design Review. More specifically, we'll cover 4 topics. First, what a 2-to-1 multiplexer is and what it's used for. Second, how to design a 2-to-1 MUX. Third, we'll discuss what a 4-to-1 MUX is and why designing larger MUXes is not as simple as writing one big truth table. And finally, we'll go through how to design a 4-to-1 MUX by combining smaller MUXes together in a clean, modular way. Alright, let's get started. So, what is a 2-to-1 MUX? Well, a 2-to-1 MUX is a simple piece of combinational circuitry that takes in 3 inputs and produces 1 output. The 2 main inputs are A and B, and the third input is the select line, S. Here's how it behaves. When S equals 0, the output is A. And when S equals 1, the output is B. So, the select line decides which input gets passed through to the output. So, to make sure you understand how a 2-to-1 MUX behaves, let's go through an example. Suppose A is 0, B is 0, and S is 0. What will the output be? Well, since S equals 0, the MUX selects A, which makes the output 0. Now let's do another example. Suppose A is 1, B is 0, and S is 0. What will the output be? Well, since S equals 0, the MUX selects A, which makes the output 1. Just to make sure you understand, let's do one more example. Suppose A is 1, B is 0, and now S is 1. What will the output be? Well, since S equals 1, the MUX selects B, which makes the output 0. So now that you know how a 2-to-1 MUX behaves, how do we actually design it? Well, the first step is to define its truth table. Since a 2-to-1 MUX has 3 inputs, A, B, and S, there are 8 possible input combinations. So we list all 8 cases, and for each one we write down the correct output. When you work through those 8 cases, you end up with the truth table shown here. Now that we have the truth table, the next step is to solve for the Boolean expression using the workflow from Section 2.1. If you need a refresher on that process, go watch the previous lesson on truth tables and K-maps. But in short, here's what we do. First, we take the rows where the output is a 1 and map them into the K-map. Second, we circle the ones using the grouping rules. And third, we convert each circle into a Boolean term and combine the terms to get the simplified expression. When we do that for the 2-to-1 MUX, we get the following Boolean expression. And once we have the Boolean expression, drawing the schematic is straightforward. We create one AND gate for S' and A, another AND gate for S and B, and then OR those two results together. So now we have the complete gate-level schematic for a 2-to-1 MUX. So what about a bigger MUX? What you're seeing here is a 4-to-1 MUX. It behaves the same way as a 2-to-1 MUX, it just has more inputs, and it uses 2 select lines instead of 1. The inputs are A, B, C, and D, and the select lines are S1 and S0. Here are the selection rules. When S1 and S0 equals 0, 0, the output is A. When S1 and S0 equals 0, 1, the output is B. When S1 and S0 equals 1, 0, the output is C. And when S1 and S0 equals 1, 1, the output is D. So the select lines are simply choosing which one of the 4 inputs gets passed through to the output. So how do we go about designing a 4-to-1 MUX? You could try to do it the same way we designed the 2-to-1 MUX, by writing a truth table and solving for a Boolean expression. But for a 4-to-1 MUX, that approach stops being practical. Once you include the 4 data inputs and the 2 select lines, you end up with a 6-variable truth table, which means 64 rows. And converting that into a Boolean expression would require a 6-variable K-map. And those are so large and time-consuming that they're basically never taught or solved by hand. So instead of designing a 4-to-1 MUX from one massive truth table, we design it the smarter way, by combining smaller MUXes together using modularization. By assembling multiple 2-to-1 MUXes together in this pattern, we can build a larger circuit that has the exact same behavior as a 4-to-1 MUX. So instead of writing a massive truth table, we simply reuse the 2-to-1 MUX block we already understand, and connect several of them together in a clean, modular way. And once they're assembled like this, the overall circuit behaves exactly like a 4-to-1 MUX, where the select lines choose which one of the 4 inputs gets routed to the output. This entire process is called modularization, and it's one of the main reasons complex combinational designs are possible. Alright, so that's all for this lesson. Thanks for watching, and I'll see you in the next one.